Hi guys and welcome to Study Project. Today we're covering International A-Levels A2 Chemistry Unit 4 and the topics today are techniques to measure rate, rate constant, orders, and rate determining steps. So let's get into it. So what is rate of reaction? Rate of reaction is the change in concentration of a species divided by time for change to occur. A species is an atom or molecule or ion that takes part in a chemical reaction. But what rates can you have? You can have an increasing rate and you can have a decreasing rate. So an increasing rate is when the concentration of the product increases with time, whilst the decreasing rate when the concentration of the product decreases with time. As you can see here, there are two equations that represent both of these rates, but for the decreasing rate, there's a negative sign in front of it. And for all reaction rates, they are positive, even the decreasing rates. This is because negative sign and a negative sign equal to a positive. And the units for rate is moles per decimeter cube per second. But what is rate constant? Rate constant is the proportionality constant that relates rate of reaction to the concentration of the reactants. As you can see here, we have a proportionality where rate is directly proportional to the concentration of a species, for example, represented by A. And these square brackets are important and you must write square brackets, not round brackets. This is because square brackets represent the concentration of a compound, whilst round brackets represent grouping of atoms together. So you can see here that we change this proportionality into an equation, into an expression. We substitute K as the proportionality constant. So that means we have rate equals to K multiplied with this concentration of the compound. What affects rate constant? This can be two things: temperature and activation energy. So how does temperature affect rate constant and the rate in general? So an increased temperature increases the rate constant and increases the rate overall. And how does activation energy affect rate constant and the rate? So when activation energy decreases, this increases the rate constant and this leads to an increase in the rate. What affects the rate of a reaction? There are two things that can affect the rate of a reaction. These are rate constant, which depends on temperature and the activation energy of the reaction, and the concentration of the reactant. But this depends on the order of the reaction, and we'll get into what this means. For all cases, the larger the rate constant, the higher the rate. In this table below, list some orders that we have to know and their effects on the rates if you do something to the concentration. So let's start with first order. Let's see if you can see a pattern here. So for first order, when the concentration of the reactant doubles, this leads to the rate of the reaction to double as well. But for second order, if the concentration of the reactant doubles, the rate of the reaction will quadruple. And for the zero order, if the concentration of the reactant doubles, this means that the rate of reaction will stay the same. But what are orders? An order is the power to which the concentration of the species is raised in the rate equation. A rate equation is the equation that expresses a mathematical relationship between rate of a reaction and the concentration of the reactants. For example, up here you can see what a rate equation looks like. Rate equals to the proportionality constant little k multiplied with the concentration of A, which is a species, to the power of m. And m is what an order is called. And what are the following orders you can have? So these are the main ones that you have to know, although there can be others, for example the third order. But the main ones you have to know is the first order, the second order, and the zero order. So again, mentioned before, for the first order, if the concentration of the reactant doubles, the rate of the reaction doubles. And the rate equation for the first order is rate equals to little k multiplied with concentration of a species to the power of 1. This basically means that for the first order, rate and the concentration are directly proportional to each other. And for second order, if the concentration of the reactant doubles, the rate of reaction quadruples. And the rate equation for this is rate equals to little k multiplied with concentration of the species to the power of 2. And for zero order, if the concentration of the reactant doubles, the rate of reaction remains the same. And so the rate equation for this case would be rate equals to k, little k. Or you can write rate equals to k multiplied with the species to the power of 0. However, we know that if something's to the power of 0, it will equal to 1. So at the end, it's cancelled anyways. So for zero order, it's just rate equals to little k. And what are the graphs that are involved with orders? So the first graph you can have is the concentration against time graph. So the concentration is on the y-axis and the time in seconds is on the x-axis. So let's go through them together. So for the zero order, you can see that the gradient is constant. This means that there's no effect on the rate here and the half-life decreases. I'll explain what half-life is in a second, but let's go through the others. So first order is when the gradient starts to increase. This means the rate increases as well and the half-life is constant in this case. And for the second order, this order, you can see the difference between the first order and and the second order because the second order has a kink in it, which is this extra bendy area. And then for second order, the gradient has a greater increase. The rate increases exponentially and the half-life increases instead. So what is half-life? Half-life is basically the time taken for a concentration of reactant to halve its initial value. So you can see in this image, like it starts off with 12, goes down to 6, and then it goes down to 3. But how do you calculate rate from this concentration against time graph? In this case, the rate is the gradient. So first thing you want to do is you want to draw a tangent to the curve. But as you can see in the zero order, there's no curve. That means there's no effect on the rate here. After this, you want to measure x and y, and then you want to use the rate equation, which I mentioned above. The rate equation meaning the change in concentration divided by time. And here's another set of graphs for order. So you have the rate against concentration graph, where the rate is on the y-axis and the concentration is on the x-axis. So let's run through them again. So zero order, you can see, is a horizontal line. This means that when concentration increases, the rate is unchanged. There is no gradient here. But for the first order, it's a straight line through the origin. So you can see here, the concentration increases and the rate increases directly proportional to the concentration. This is a linear and a constant gradient. And for the second order, you can see that there's a bend in this graph. So you can see as the concentration increases, the rate increases exponentially. And this means it's a non-linear increasing gradient. So what are some units for K? Proportionality constant for each order because they are different for each order. So things you want to remember in this case is the units for rate and the units for concentration. So the units for rate is moles per decimeter cube per second, and the units for concentration is mole per decimeter cube. So let's start with the first order. First thing you want to do is you want to write out the rate equation for each order. So the first order is rate equals to little k multiplied with the concentration of the species. As you can see here, the units for this is per second. So but why? First order, you want to write out the rate equation again, and you want to rearrange it so you make k the subject. Instead of writing r and the species concentration, I want you to substitute the units for both and write it out. And after you write it out, you can see the similarity between the top and bottom. As you can see in this case, on the top and the bottom, there is both moles per decimeter cube. And since they're the same, you can just cancel them out. In the end, you are left with per second. And for second order, we write the rate equation again, which is rate equals to little k multiplied with concentration of the species to the power of 2. And as you can see here, the units for this case is decimeter cube per mole per second. So why is it this? Again, you want to rearrange the rate equation so that k is the subject, and you want to sub in the units for both rate and for both the concentration. As you can see here, is to the power of 2. We know that if something's to the power of 2 is basically multiplied by itself another time. So that's why we do moles per decimeter cube multiplied with moles per decimeter cube, because this time there are two of them. And again, you want to cancel out the similarities. So in the end, we are left with k equals to per second divided by mole per decimeter cube. And if you rearrange this, then this eventually leads to k equals to decimeter cube per mole per second. And finally, for zero order, we write the rate equation again. Rate equals to little k multiplied with the species to the power of 0. Basically, rate equals to little k. And then you want to rearrange this so that k equals to rate divided by the concentration of the species to the power of 0. And again, as I mentioned, something to the power of 0 is equal to 1. So you substitute 1 in this case, and that means that k is basically equal to the same units as rate. But what is overall order? An overall order is the sum of all individual orders in a rate equation. An example is rate equals to little k multiplied with first order A, first order B, and second order C. And this means that the overall order 4. How do you determine the rate equation? There are two methods to determining the rate equation. You have the continuous method and you have the initial rate method. How do you do continuous method? Continuous method has the following steps. So first thing you want to do is you want to take aliquots. Aliquot is basically a sample from a larger mixture. So you want to take samples or aliquots from reaction mixture at regular time intervals, for example, at every 3-minute time intervals. And then you want to quench the aliquot using an ice bath or a substance that can neutralize it. And then you want to determine the concentration by using titration. And then you want to repeat this with the other aliquots that are taken. Plot a concentration and time graph and find the half-life to determine if it's a zero order, first order, or second order. How about for initial rate method? In initial rate method, it uses several reaction mixtures and it basically calculates the order of each species by using a mathematical relationship for rate and the concentration of reactants. In this table, you can see the different experiments that represent the different reaction mixtures. However, the difference in the reaction mixtures is just the concentration of each species, as each reaction mixture has the same reaction species. And we can see its effect on the rate of formation of C, which is the product in this case. I want you guys to figure out what A and B orders are, and then from this determine what the rate equation is. So for A is first order, but why is this? If you look at experiment 1 and experiment 3, you can see that A concentration doubles, but the B concentration stays the same. And you can see that the effect on rate is that it doubles. So that means the only thing that affects rate in this case is A. And this means it's first order because as A doubles, the rate also doubles. And for B is also first order because if you look at experiment 1 and experiment 2, you see that in this case it's the reverse. So concentration of B doubles whilst the concentration of A remains the same. And this in turn leads to the rate doubling. So this means that because A stays the same, the only thing that's affecting the rate is the concentration of B. And when the concentration of B doubles, the rate doubles. So the rate equation overall is rate equals to little k multiplied with the first order of A and the first order of B. On to a common question. What are the orders of these species? You guys can pause the video here and try to figure out what the order of these species are. So let's get started. Bromide is a first order. But why is this? Because as you can see in experiment 1 and experiment 3, bromide concentration triples whilst the concentration of bromate and hydrogen ion stays the same. And as you can see for the initial rate, as bromide triples, the initial rate also triples. This means that bromide is the first order because its change directly affects the initial rate. Bromate is the first order because if you look at experiment 1 and experiment 2, bromate doubles in concentration while the other species concentration remains the same. And as you can see, the rate also doubles. This means that bromate is a first order. And as for hydrogen ion, in order to work out hydrogen ion, we have to look at experiment 1 and experiment 4. So as you can see in experiment 4, there are two species that have a change in concentration, bromide and hydrogen ion. So the first thing you want to do in this question is you want to work out the order of one of them first, one of the species first. And we have already done this because we worked out the order of bromate already, which is first order. And as we know, first order, if a concentration doubles, then the rate will also double. So that means starting with 1.2 times 10 to the minus 3, and since bromate doubles, this means since it's a first order, the rate will also double to 2.4 times 10 to the minus 3. However, in the fourth experiment, the initial rate is not 2.4 times 10 to the minus 3. Instead, it is 9.6 times 10 to the minus 3. That means that hydrogen ion has an effect, and that means the order of hydrogen ion is not the zero order, because otherwise the rate would be 2.4 times 10 to the minus 3. This means that we can divide 9.6 times 10 to the minus 3 with 2.4 times 10 to the minus 3, and we will get 4. This means that when hydrogen ion doubles in concentration, the effect it has on the rate is by times 4. This means that when concentration of hydrogen doubles, the initial rate would then quadruple, resulting in the hydrogen ion to have a second order. For the next question, I want you guys to work out the rate equation of this reaction and what are the units for K and what is K. So you guys can pause the video again here and using your knowledge of the previous orders of these species, write out the rate equation and then from that calculate what K is. So first thing you want to do in this question is you want to write out your rate equation. Again, the rate equation is rate equals to the proportionality constant multiplied with the concentration of the species and its order. In this case, we know that hydrogen ion is a second order, bromate ion is a first order, and bromide ion is a first order. So our rate equation is rate equal to proportionality constant multiplied with second order hydrogen ion multiplied with first order bromate ion multiplied with first order bromide ion. The next thing you want to do is you want to work out the units for K and you want to work out what K is. First thing you want to do is you want to rearrange so that K is the subject and then you want to substitute. You can use any of the equations, but in this case I used equation 1. You can use any of the experiments, but in this case I use experiment 1 and substitute the concentrations of each species and always make sure that you have the powers sorted. In this case I didn't put it to the power of 2, however I wrote it separately out. So I did 0.1 times 0.1 times 0.1 times 0.1, so 4 times. And I did the rate divided by this, which I got 12. And to work out the units for K, you repeat this substituting process. However, instead of substituting numbers in, you substitute the units in instead. And in the end, it works out to be 12 dm9 per mole cube per second. But what are some techniques that are used to measure the rate of reaction? We have a volume of gas evolved, change in mass, change in color intensity, change in concentration done by titration, change in electrical conductivity, and finally change in pH. So let's start with volume of gas evolved. There are two ways to do this. You can either use a gas syringe or an inverted measuring cylinder. Both of these have their own cons and pros. So let's discuss the gas syringe one first and why it is more efficient. So we use a gas syringe in this first image, as you can see, to obtain very precise measurements of the gas evolved. However, the con or the disadvantage of this is that only a small volume of gas is measured, meaning like a smaller measurement is obtained, and this could possibly lead to a higher percentage uncertainty. However, for the inverted measuring cylinder, the pros for this is that large volumes of gas can be measured, but this is only effective for insoluble gases. For example, it cannot be used to measure carbon dioxide, sulfur dioxide, and ammonia. These are soluble gases. And another reason why it's a disadvantage compared to gas syringe is that it gives less precise measurements due to a measuring cylinder not being as accurate as a gas syringe. Another thing you have to note is that to measure the rate, you have to do the volume of gas evolved divided by the time taken. Onto change in mass. So to measure the rate, you have to do the change in mass divided by the time taken. In this case, the change in mass is the decrease in mass. This is because if there's a gas evolved from the reaction, it can leave the conical flask, basically resulting in less mass in the conical flask, and this is recorded. But what type of gas works best for this type of technique? So highly dense gases are what's best for this technique. For example, carbon dioxide. This is because the change in mass will not be negligible. This means that, let's say, carbon dioxide is produced in a reaction and carbon dioxide escapes the conical flask. This means that there will be a more significant change in mass. Finally, what is the purpose of the cotton wool? The purpose of the cotton wool is to prevent loss of acid splash or acid spray, basically meaning that only gases can escape and no liquids or other things can escape. Next, we have changing color intensity. There are two methods you can use. You can use observation. This is less accurate, but it is quicker. Or you can use a colorimeter, which is more precise. A colorimeter can detect far more subtle changes, and this can provide quantitative measurements. And this basically means it's better for comparison and it's not biased. So an example situation is iodoform test, where propanone reacts with iodine. As we know, iodine is a colored species. It is a brown color. And after this reaction occurs, this ground color becomes colorless. The brown color decolorizes. This means to find the rate, you have to measure the time taken for the color to change. The shorter the time, the faster the rate. On to the next. Change in electrical conductivity. This basically means that there's a change in the total ion number. How can you measure this? You use a conductivity meter. An example situation is this example below, where you can see on the left hand side, these are where all the ions are present, but on the right hand side, there are no ions. So you can see there's a change in the total ion number. This means that on the left side, since there's more ions, there are more ions to conduct electricity. On the right side, there are no ions, so there's no electrical conductivity on this side. Change in pH. Instead of ions, this is specific to hydrogen ions. So again, we can measure this using a pH meter, and we can use the same example because as you can see here, there are 6 hydrogen ions on the left side and no hydrogen ions on the right side. This means there's a lower pH on the left side. This is because the more hydrogen ions, the lower the pH, meaning the more acidic it is. On to the next one, change in concentration using titration. Again, we can use the same iodoform test example where propanone reacts with iodine. But what are the steps on how to find the change in concentration using titration? So first thing, you want to use a pipette. Pipettes are more accurate than measuring cylinders. So you use a pipette to remove allocoids, which are small samples taken from a bigger sample, and you want to remove these allocoids from the reaction mixture at regular time intervals. For example, every 3 minutes at least 5 times. Then you want to quench, which means to slow or stop the reaction process. You want to quench the allocoids using either an ice bath or another substance that can neutralize. This allocoid is then titrated with an appropriate solution to determine the change in concentration. In this example, iodine and propanone are catalyzed by an acidic catalyst. To quench this allocoid, you use sodium hydrogen carbonate to neutralize the acidic catalyst. Then you want to titrate this allocoid with the standard solution of sodium thiosulfate, and then from the titer, you want to work out the concentration. So there are 2 different types of reaction mechanism. You have elementary and you have non-elementary. So what is elementary reaction, or what are elementary reaction mechanisms? So this is a single successful collision between reactant particles, and these reactant particles collide with correct orientation. If we know that this reaction is an elementary reaction, then we can deduce the mechanism and the rate equation from the stoichiometric equation. It is a one-step reaction. In the example below, you can see that P and Q are the reactant species, and when they react together, they form these products. Since it's an elementary reaction, we can deduce the rate equation and assume that both of them are first orders. This is why the rate equation is rate equals to little k multiplied with the first order of P and the first order of Q. On to the next one. What are non-elementary reaction mechanisms? So in this case, it is not possible to deduce the mechanism or the rate equation from the stoichiometric equation. This is because there's a series of interconnected elementary reactions. It is not just a one-step reaction. In this case, there are many step reactions that can produce intermediate. Intermediates are products formed in some steps that are not in the rate equation but help the following reactants to make the following product. And it involves a rate determining step. And I'll explain what this means in the next slide. But let's talk about this example below. So in this overall equation, we have nitrogen dioxide added with carbon monoxide to form nitrogen monoxide and carbon dioxide. So the rate equation in this case is rate equals to K multiplied by nitrogen dioxide squared. But how do we get to this rate equation? Because we can't determine this rate equation from the stoichiometric equation. The first thing we have to do is we have to run through all the steps and we have to determine which one is the rate determining step. In short, rate determining step is basically the slowest step. So you can see here that the first step, the 2 molecules of nitrogen dioxide step, it is the slowest step. So in this case, this is the rate determining step. However, to double check this, as you can see in the bottom where all the colorful lines are, how do you even get to the overall equation? So from this step, you can determine the similarities on the left side and the right side. And if they are similar on the left side and the right side, then you can cancel them out. The overall equation is whatever's left that's not cancelled yet in these steps, which is why the nitrogen monoxide and carbon dioxide are the products in this case. As you can see here, in the rate determining step where the 2 molecules of nitrogen dioxide react together to form nitrogen monoxide and oxygen, nitrogen monoxide is one of the products. However, oxygen is not a product. Oxygen here is the intermediate. And as you can see here, oxygen reacts with the other reactant, which is carbon monoxide. In this case, this is not the rate determining step, and this is not a step that is involved in the rate equation, because the only thing that's involved in the rate equation are the reactants that are involved in the rate determining step, which is the first step, the slowest step. This intermediate, the oxygen intermediate, reacts with this carbon monoxide to form the other product, which is carbon dioxide. And that is why the rate equation is rate equals to little k multiplied with nitrogen dioxide squared. But what is the rate determining step? It is the slowest part of a reaction that controls the overall rate of a reaction. It is basically the step that produces an intermediate. As you can see in the example below, we have the overall equation, which is A plus B plus C equals to D plus E. So in this case, the rate equation is rate equals to little k multiplied with first order of A, first order of B, and 0 order of C. If it's a 0 order, that means this is not used in the rate determining step. And actually, since it's a 0 order, you don't have to mention it in the rate equation at all. However, I wrote to the power of 0 just to make it more visual. That means since C is not involved in the rate determining step, it is still used to react with the intermediate formed. So as you can see, the species that are involved in the rate determining step, A and B, form an intermediate, and this intermediate then reacts with C, which is the 0 order species, to form D plus E. Thank you for watching, guys, and stay tuned for more videos to come.